Oh boy, what we have got into. So we have derived an extensive set of equations, and these equations are intimidating if you don't understand them conceptually, and we have done that for the uniaxial PML that we are going to model in the Matlab environment. Before I jump into the Matlab code itself, I would like to recap the final set of equations that we need to model this particular problem. So let's look at this set of equations and get an overview of it, and we will go into the Matlab model. So we have got 1, 2, 3, 4, 5 set of update equations, and we have got the flux terms that are due to the standard Maxwell equations for 2D problem, which is marked in blue here, and we have got two additional equations because we are talking about X and Y oriented uniaxial PML, and the green terms what we have got here are the uniaxial XPML loss terms. So these are the loss terms that we are going to have. So now let me describe the problem that we are going to model using a simple diagram. What we have got is a square domain. So the domain itself is going to be, let's say, 50 by 50, some arbitrary units. It could be meters, it could be centimeters, depending on what you are interested in. Let's say it's going to be 50 by 50, and I have a point source which is located here, and I have got a scatterer which we have modeled it as a small square as well. It's going to be a perfect electric conductor, and now we are going to truncate this particular domain using uniaxial PML that are both X and Y oriented. So if you assume this is the X and this is the Y axis, and the Z is coming out of it, out of this paper. So what we have got is the waves that are going to come. So these are going to be the sinusoidal point source, point source, and this is going to be the PEC scatterer, perfect electric conducting scatterer. And how do we run this problem? We are going to simulate this problem by truncating this domain using two sets of PML. So I am going to draw them like this. So what we have got here is both the X PML, this is also X PML, and we have got both the Y PML. So this is Y PML and this is Y PML, and here we have got both the X and Y oriented PML. So this is going to be both X and Y UPML. Important to know is when we are truncating a problem using PMLs, we have to truncate the PML itself. It is not just enough to put a PML around it. The question comes, what is going to be that is going to be at the end of the PML? So we are going to use perfect electric conductor, PEC. It's going to be PEC that is going to sit on all the PML backside. So PEC is here. So the question about PEC is the tangential component of the electric field goes to 0 there. So that's something that we have to look into, and we'll see how we are doing that in the Matlab code. So this is going to be our problem geometry, and let's go and look into the Matlab code itself. So this is going to be the Matlab code that we are going to run. So the code is to study the scattering of electromagnetic waves from an object where the domain is truncated using UPML, uniaxial PML. So as I said, we are defining the physical domain, we are setting its dimensions to be 50 and 50 on the x and y direction. We are setting certain physical constants epsilon naught and mu naught, which are the permittivity and the permeability of free space. We are setting the source parameters, so the velocity of electromagnetic wave propagation, the frequency. So we are taking a frequency of 30 megahertz. It does not matter what you are choosing here for this particular simulation, we can go also higher frequency, but accordingly the parameter for discretization will change. So this is going to be the number of cells that are going to be there for a particular lambda. There should be at least 20 cells that should be sitting within a particular lambda, and here the lambda value is calculated based on this equation, which is C divided by frequency. So Nx is going to be the length of the x step and Ny is going to be the length of the y step. The source location we have assigned it to be Nx by 2 and Ny by 2. So it is going to be more or less in the middle. So the simulation time has been set to 200 time steps, and we have set the CFL parameter R to be 0.5. Of course you can go until 0.7 for this kind of problems, but we have set it to 0.5 so as to make sure that we get a stable simulation, and accordingly we can get the delta t, which is going to be the time discretization parameter. We have set the value for the profile of the PML to be 2. So I will explain you what it means in this particular illustration. So what we will get is normally a PML that is going to start. So let us say we are talking about only a x oriented PML, and this is going to be the starting point of the PML. Let us say x start, and what happens is the conductivity sigma x is going to have various values across the entire PML. So what you can say is it can either have a constant value, so between x start and xn sigma x is equal to constant is going to be one of the options which we can choose, or we can say sigma x is going to vary linearly within the PML. So this is x PML, it is going to vary linearly, the value of sigma x is going to vary linearly, where the value will be minimum at the starting and maximum at the end, or we can go for parabolic value. So it is going to have a kind of a curve. So this is going to be, for this is sigma x equal to 0 for a constant, so the profile will be 0. Profile is going to be 1 for the linear variation and profile 2 for the parabolic variation. Of course you can go higher order, but we have chosen a parabolic profile inside the PML. We are not going to use this particular term theoretical reflection. Of course you can compute the value of the maximum value of sigma inside the x and y PML using the theoretical reflection. I am not going to do that here because it is involving a bit of more complex illustration in the mathematics. For now we will assume the value of maximum sigma in the x and y direction going to be 0.01. So we take it as a face value. Of course there is a way to derive this using the theoretical reflection that one needs to achieve. So let us not go into it. For now we will choose sigma x maximum and sigma y maximum is going to be 0.01. And we are considering the thickness of the PML to be 8 cells. So there are going to be 8 cells inside this PML. So this is 2, this is 4. So there are going to be 8 cells that are going to sit inside the PML. Of course you can vary this, and I wouldn't do it too much, because the idea of putting the PML is to bring the boundary closer and closer to the actual domain of interest. If you increase it, it's going to increase also the computational cost. So keep it between 10 to 15 ideally. So we said there is going to be both the left and right XPMLs. So that means in our problem what we have here, there is going to be both the left and right XPML, and there is also going to be low and up PML. So there is going to be a low YPML and a up YPML. There is going to be a left XPML and right XPML. So that is the parameter what we are describing here. If I put 1 1 1 1, it means all the 4 sites are covered by PML. So initially I declare sigma x and sigma y to be 0. I declare mu r and epsilon r, relative permeability, relative permittivity to be 1s, and I declare the value for mu and epsilon to be 0, and the impedance value for the space that we are interested in is also declared at 0, and we are going to go inside the equations. There are some values that we declare just for us to use them inside the equation, but it's not important for now. So I find out what is going to be the conductivity value. So the value that I have to assign into the PML. So if you see here, I said it's going to vary in a parabolic manner, but I have to know what is going to be each of the value at this point, 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 this point. So I'm saying the value inside each of the cell is going to depend on the x and y coordinates of that particular cell. So I'm going to take the first edge of that particular cell and see what are the x and y coordinate of this particular cell. So if I have I can write it in an elaborated manner. So if there are going to be different cells, initially I take this particular point and ask what is going to be the x or y value. The x value is important when I am talking about the x oriented PML. The y value will be important when I am talking about the y oriented PML. The moment I know the x and y coordinate, I can assign the value for the conductivity using this particular equation. So I am saying the value for the PML sigma x equal to the sigma naught x, the maximum value, multiplied by dPML minus the coordinate I multiplied by dx. This is going to give me my x value. So there should be a bracket here, divided by dPML multiplied by dx, the whole square. So I have chosen the second order profile, so I am using the square here, and you can in fact cancel the dx. What you will get is sigma x is equal to sigma naught x multiplied by dPML minus I divided by dPML whole square. So this is what we are seeing in this particular equation here in the code. You see sigma x naught is the maximum value, and I am finding out what is the position of the cell from the thickness. I am subtracting that value, so I will know the position of the cell with respect to the thickness. The maximum value will be at the distance dxPML, which is the length of the PML, and the minimum value will be at the point where the PML is starting. So when I is the first one, so it will have the minimum value. When I is equal to dxPML, it will have the maximum value. So now you can do the same thing for other domains. When you are going to the when you are going to the left oriented XPML, what you need to do is you need to swap this as I minus dxPML. instead of dxPML minus I, because there the starting point will be on the first one and then the ending point will be on the left hand side. What I mean is, if you go back here, if there is going to be also an X oriented PML but on the left hand side, so the first point here, the rightmost point of this PML will have the lowest value and the leftmost point will have the maximum value. So the value is going to go down, whereas here the leftmost point will have the minimum value and the rightmost point will have the maximum value. So you have to swap it, and that's why we have swapped this particular term also. So this you can see while you go into the code. And what we are doing is we are also assigning the value for mu r, epsilon r for the particular thing. Remember, we have declared this one as 1, so we are doing it for free space where the epsilon r and mu r are taken to be ones, because we have declared them as ones in this particular step. So if you see here, these are the values that we have declared as ones, and we are going to initialize the fields. We are setting the boundary conditions. I said all the boundaries of the PML are going to be truncated using the perfect magnetic conductor or perfect electric conductor. And what you are seeing here is we are defining the scatterer. So the position of the scatterer is going to be defined by this particular equation. So the scatterer is the one which we are having here, and we are saying that the source value is going to be at this point, and we are assigning it to the EZ component here, and they are going to be exactly in the middle. So now we are going to set up the boundary conditions for truncating the PML itself. So we said we will go for a PEC condition. We are putting the tangential component of the electric field and the normal components according to the position of the magnetic field to be 0, and we are defining the scatterer not initially, although we can look where the scatterer is going to be. Initially when we are running the program, we are not going to define the scatterer, so these are commented now, but we have shown where the scatterer is going to be using a rectangle that is marked in the magenta color. So it is going to be the position. So when we are going to simulate it for the first time, you will see that there is a scatterer position, but the scatterer is not defined. The moment we define the scatterer, we have to put the tangential component of electric field to be 0, then it will act as a perfect electric conductor, but for now we have commented it. And the calculation for Hx, we will have Kx component, the calculation for Hy, we will have the Ky component, and we have the Ez component, and we keep updating it. And the source location is exactly in the middle. We have taken twice the magnitude of the source just as to increase the contrast in the simulation, so as to have a high amplitude. So let us now simulate this particular program and see what we can expect from this particular simulation. So what you are seeing here is there is a point source, and this is the location of the scatterer. As I said, right now it is not a scatterer, it is just a marker. So you see the wave is moving through it without any scattering, and the PML starts from this particular point. You see that it starts to decay and slowly starts to disappear, what is getting absorbed, and the field is going unaffected by the scatterer. As I said, it is still not a scatterer, so the field is getting unaffected by the location because it is still not defined as a scatterer. So now we will go back to the code and we will define it as a scatterer by uncommenting this particular point and run the same code and see what we can simulate using this particular situation. Now it is a perfect electric conductor, so it is going to reflect everything that is impinging on it. So you can see it cuts the incoming wave is getting bifurcated using this particular scatterer, and you can see that the XPML is absorbing whatever is incoming, the YPML is absorbing, and the complex domain is also absorbing, and we have PEC on all other sides. So we can test such a problem for various applications. So what I would recommend is you take this particular code, practice it for yourself, simulating it for various problems, and as I said before, the source of this particular code comes from the theoretical discussions that has been presented in a phenomenal paper written by Gedney, an anisotropic perfectly matched layer absorbing medium for truncation of finite difference time domain lattices. It was published in 1996 in the IEEE transaction on antennas and propagation. So with this, what we have done is we have showcased a very important point that one needs to learn if one says he is doing computational electromagnetics or computational modeling, which is nothing but the perfectly matched layer, domain truncation. We will be using this over and over again in various methods that we are going to apply, or the various methods that we are going to learn. So it is important that you get a good grip on this particular method, and that too using finite difference method. Later on, when we do finite element, finite volume, so on and so forth, we will come back to it again and again, and even in the method of finite volumes we will discuss much in detail about the implementation of such methods. But for now, I think we have covered the most important aspect that I promised that I will cover. I request you to take this code and practice it for yourself, see for yourself how you can model it, and also I encourage you to write your own code. So don't take this code directly. Of course we wanted to give you the code, but we are also afraid of giving codes, because sometimes people take the code and simulate it and it's just a black box for them. In some cases what we will do is we will genuinely avoid giving codes so as to make you learn and make you program, and that's the intention. So if you are failing in coding, that means you have not learned computational electromagnetics in its entirety. So we would like you to learn to code. So in that sense, sometimes we ask you genuinely to code. This particular exercise is an excellent example for you to practice coding. So I encourage you to do that. And that being said, we have come to the end of this interesting long module. So we will stop here, and we will look at some of the applications of the PML in the following lectures as well. And if you have any specific questions, please post your questions on the forum. We will be very happy to answer those questions and help you understand the perfectly matched layer technique. Thank you.